As we continue learning about different topics related to the broad field of mechanics, we also introduce new tools and methods for problem solving. We have the tools of Newton's three laws of motion and the kinematic equations, but sometimes there may be variables that we do not have good values for and yet have problems we need to solve. Momentum and energy provide alternative solution processes that can be added to the ever-growing tool belt of resources for solving problems. Module 2 includes one last throwback to the problem-solving tools from Module 1. Chapter 5 looks at problems that involve circular motion, referring back to one of the course competencies first introduced in Module 1. It looks at how such motion is caused by forces acting on an object at right angles to its motion, what we call centripetal forces. Centripetal motion comes into play when dealing with topics in astronomy, for example. Newton's universal law of gravity is a defined force, a force with specific variables that define its strength. It is considered a centripetal force in some problems as it is the force that can keep astronomical bodies orbiting other astronomical bodies. In Newton's second law, it would be the force on the sum of forces side, complemented by the centripetal acceleration, or more specifically radial acceleration, introduced in this chapter. Historically, Newton used his laws of motion and universal law of gravity to derive a set of planetary orbit laws known as Kepler's three laws of planetary motion, which are introduced in this chapter. Kepler developed these solely from observation with no underlying explanation other than they worked. Years later, Newton would derive these three laws from his laws of motion and universal law of gravity, establishing gravity as the central force responsible for orbital motion seen throughout the universe, well beyond just the solar system of planets and their satellites. The concept of energy is introduced in Chapter 6. Energy comes essentially in two forms in mechanics: stored energy and motion energy. Stored energy is referred to as potential energy. There are two types of potential energy introduced: gravitational potential energy and spring potential energy. Gravitational potential energy is the energy stored in an object due to its position above Earth's surface, and by extension, the surface of any gravitating body. Spring potential energy is that stored in a spring when it is either stretched away from or compressed away from equilibrium. Kinetic energy is the name of the motion energy. All moving objects have kinetic energy, and only moving objects. Related to energy is what is called work. Work in mechanics is quite different from the way the word is used in everyday language. Like all definitions in physics, it has a specific definition. Work is defined as the product of the net force acting on an object and the displacement of that object in the direction of that net force. Energy and work are scalar quantities, even though they contain items that have been identified as vectors. In this case, positive or negative signs are more about gains and losses, not direction of application. Tying these concepts together are two relationships: the work-energy theorem and the conservation of energy, both of which address additional competencies of this course. One of those states, solve problems using the conservation laws. The second states, solve problems using the work-energy theorem and determine associated power. The work-energy theorem says that work is done when there is a change in energy. So, work can cause a change of energy, or if energy is changed, work can be done. So if one uses a hammer to open a walnut, a change in kinetic energy, the movement of the hammer from rest to the top of the walnut, and the gravitational energy, initial height to the top of the walnut, leads to a force applied over the thickness of the walnut, that is, work being done, to crack open the walnut. Or a pitcher's arm applying a force on a baseball over the extent of the reach of that arm, resulting in a change in the kinetic energy of the baseball from 0 to some final value. If there are no external forces acting on a system, then the change in total energy of the system is 0. But even if the change in total energy is 0, either the potential or the kinetic energies, or both, can individually change so that the difference remains 0. A skier at the top of a hill, for example, may start off with both gravitational potential energy and kinetic energy at the top of the hill, but as friction between skis and snow is minimum, can have even greater kinetic energy and thus speed at the bottom of the hill. No energy losses due to external forces acting along the slope, so the stored energy at the top of the hill becomes additional kinetic energy at the bottom. The total energy remains the same. There's just a redistribution of energy between types. Momentum and impulse are introduced in Chapter 7. In this case, we return to vector quantities, so direction of momentum needs to be tracked among the different objects involved in a problem, along with any other vector quantities the problem may introduce. An impulse can change momentum of an object. Like work, impulse has a very specific definition. It is the net force acting on an object multiplied by the time the force is applied. One can have a small force act over a long time, or a large force act over a short time, and get the same impulse. Either of these situations will result in the same change in momentum of an object. If there are no external forces acting on objects for specified times, no impulses, then the momentum of the system of objects is said to be conserved. This then is another conservation law that is addressed by the competency solve problems using the conservation laws. Although the total momentum may be the same before and after an event, the individual momenta of the objects in the system may change. This is particularly useful when dealing with explosion and collision problems. In both cases, it is best to look at a before and after picture of what is happening and track the momenta of each object in the system in the before and after pictures. This then leads to equations that might be used to solve for whatever variable is important in that problem. Collisions can be divided into elastic and inelastic collisions. These in turns can be 1, 2, or 3-dimensional, and as vectors it is necessary to keep track of which part of which object's momentum is in what or more directions. Recall that these are vector quantities. Elastic collisions have the added benefit that not only is momentum always conserved, but energy, usually kinetic energy, is also conserved, which can lead to both conservation laws providing equations for problem solution. Inelastic collisions do not have that benefit of energy conservation, so that only conservation of momentum, which is always true in all collisions, may provide the necessary equations. The introduction of moments of inertia and torque in Chapter 8 allows for the expansion of problems beyond treating objects as point masses. After all, most objects we encounter in real life are not point masses, and the applications of forces to them can not only lead to linear motion, but potentially rotational motion. Torque and moments of inertia, along with rotational versions of the linear equations introduced at this point, that of kinetic energy, momentum, and the kinematic equations, and address the potential of rotational motion in the applications of torque. Torque can be thought of as a force that drives rotational motion. One of the other motion types mentioned in the course competency solve problems involving linear, circular, rotational, or vibrational motion. But the amount of rotation depends on both the applied force and where the force is applied. So torque is defined as the product of the applied force times the lever arm, the latter being the physical distance between a center of rotation of the object and the point of force application. Because we are dealing with extended bodies rather than specify the mass, one uses the inertia of the object. The inertia encompasses the mass and the shape or volume of the object. There are different formulas for determining the inertia of different objects that represent different situations, whether rotation is possible through the middle of the object or one side, or whether the object is hollow or filled. It is necessary when specifying the inertia of an object that one knows the appropriate circumstance of the problem to choose the right moment of inertia equation for that problem. In addition to rotational versions of the three kinematic equations, the application of Newton's laws using rotational variables, as well as the conservation of energy and momentum for rotating objects, are all presented. These become additional tools to be added to the problem-solving toolbox started back in Chapter 1.